what does E equals mc squared describe? What does it mean, and why is it so famous?
So E equals mc squared is just an equation that relates energy to mass. So energy is a difficult concept to pin down, but it's essentially it's the capacity of any object to make things happen, and it comes in all sorts of forms. When objects are moving, they have energy.
So when you go for a run, obviously.
Exactly, you're using energy. Then you're turning chemical energy in your body into kinetic energy, energy of motion. But one of those forms is actually mass itself. So just by an object being there and having a mass, it has energy. And this came out of special relativity. And I think there are a couple of reasons why it's so famous. One is that it's so easy to remember. It's such a short equation that it just easily kind of blends into the public consciousness, I think. But then I think another reason is that it's so closely related to the first atomic weapons, because it was E equals mc squared that allowed people to figure out the amount of energy that was going to be released by nuclear bombs.
So presumably, yes. So presumably a nuclear bomb uses nuclear energy, which is the same sort of energy in power plants, is it?
That's right. Yeah. Well, some bombs are powered by fission, which is the same as power plants.
So where exactly does this energy come from? Could you describe it? This nuclear energy.
Yes, of course. It's the particles that make up the nucleus of an atom are very strongly bound together. It would take a lot of energy to pull one of those out of the nucleus. So by having them all in the nucleus together, there's a lot of energy ready and waiting there to be released.
So what is a nucleus then?
What is a nucleus? So everything that we know of is made of atoms. Everything familiar, and atoms are composed of one type of particle, which is the electron, which is the particle that carries electricity through circuits, and those are surround a nucleus, which is right at the center of the atom, which itself is made of other particles, protons and neutrons, and the nucleus makes up most of the mass, most of the weight of the atom, but it's incredibly small in comparison.
So how small would you say is compared to an electron that's orbiting it?
Well, it's bigger than the electron orbiting it, but it's much smaller than the orbit that the electron follows. So the classic example is if you had an atom the size of an Olympic stadium, then the nucleus would be around the size of a pinhead at the center of the stadium. Or to put it another way, if you blew your nucleus up to the size of a beach ball and put that in Trafalgar Square, then your electrons would be running around the M25.
So what's kind of filling the rest of the space between the electron and the nucleus in the middle? This massive Olympic-sized stadium. What's in that space?
Well, that's it. It's nothing. There is nothing filling that space. It's empty space. The nucleus contains all of that mass, but it's in an incredibly dense form. The atom is mostly empty space, and this is actually where the idea of the incredible density of neutron stars comes from, is when we lose that empty space.
Okay, well, I want to move it on a bit. I wanted to ask you, what's the Large Hadron Collider at CERN? Because I'm sure that's related to particle physics in some way. And what does it do?
So the Large Hadron Collider is a particle accelerator. So it takes some of these particles, specifically protons, in the case of the LHC,
So protons make up the nucleus, do they?
Protons are one of the two types of particles in the nucleus.
Okay.
That's right. So the LHC takes protons and it gives them a lot of energy, kinetic energy, movement energy, and speeds them up to very, very close to the speed of light. And it sends them around these very large tunnels, 27-kilometer circumference tunnels, speeding them up using electric and magnetic fields, and it focuses them down to a very, very narrow beam and slams them into each other at very high speed, very high energy. And that much energy in such a small space can create other particles. And the idea is that we slam the protons together and we see what particles come out of those collisions.
So am I right in thinking that all this energy effectively relates back to the E equals mc squared thing, because we've got all this energy and it makes more mass? Is that kind of what's happening?
Yeah, that's the idea. So the protons have got energy because of their motion, but when we slam two protons together in opposite directions, then there is no overall momentum. So there's not going to be a great deal of motion of the things created out of that collision. So all of that energy can go into the mass of the particles that we produce instead,
rather than movement energy.
Exactly.
Okay. So what has this Large Hadron Collider achieved so far? And well, it's still running. So what are the plans for the future?
So far it's managed to constrain some of the parameters of our models of particle physics. It's given us a better understanding of exactly how strong certain forces are, and how much certain particles interact with each other. Its biggest achievement, arguably, it's certainly its most famous achievement so far, is its discovery of the Higgs boson.
So what is the Higgs boson? Is that
good question? so the Higgs boson is essentially a leftover from what's known as the Higgs mechanism, and this is the mechanism that gives all of the other particles their mass. So we can imagine, if we imagine a field that runs all the way through through space. If we're at very high energies, like in the early universe, then that field could have different values. It could have positive, negative values at different places. It all averages out to 0. As we lower the energy, what we find is that field has the same value everywhere. So if we've got this kind of non-zero field everywhere that other particles are trying to move through, then if they interact with that field, it makes it difficult for those particles to move. And that's what we see as the particles having mass.
So basically the particles having difficulty moving through this strange field is what gives it mass,
yes,
broadly speaking.
Yes. And then the Higgs boson itself is actually just a leftover, kind of a remnant of that process. So it's the residual oscillations of that field around this constant value that it's picked up.
So I do believe that the Higgs boson belongs in something called the Standard Model. So I was going to ask you, what is the Standard Model?
The Standard Model is so far our best understanding of particle physics. It contains all of the different particles that we know of, and all of the different ways that those particles can interact with each other. It was developed, I think, in the 70s, but we know that even though it's very accurate and it describes most of what we currently understand, we also know that it's not complete. There are problems with the Standard Model, and there are things that it doesn't describe.
Because from my knowledge, I do remember seeing the Standard Model and being shown this big table with loads of numbers in it. Is that what it is, or is that something else?
That's well, yes. I mean, the different interactions of the different particles is essentially the Standard Model. So it's a list of the interactions that are allowed, and a list of how strong those different interactions are. So that big table that you saw probably consisted of a number of particle names, and probably a list of numbers, I think 19 numbers, that characterize all of the different interactions that are allowed.
So why is it called the Standard Model, this table of numbers?
Well, it's standard in the sense that it's what we use most of the time. It's a very accurate model of what particles exist in the universe, so it's what we fall back on most of the time. As I say, we know it's not the complete model. We know that there are things, as we say, beyond the Standard Model. But for everyday calculations and understanding everyday phenomena, then this is the model that we'd use.
So I do have a question about those things I saw in the Standard Model. Well, can you weigh everything in the Standard Model?
Can you weigh everything? Well,
can you pick it up and look at it and say this is the mass of it? Is that possible?
So I mean, these things are incredibly tiny. So you wouldn't measure their mass in the usual sense using a scale. What we do is we use these collisions, like at the LHC, to measure the energy and the momentum of particles when they collide with each other, and from that we can figure out what their mass must be. And what we find is that yes, we can figure out the mass of all these different particles with a certain amount of uncertainty around the value that we find.
So, what are antiparticles, and do you find them in the Standard Model? Are antiparticles part of it?
Absolutely, yes.
Are they real particles? Because anti makes it sound like it's not a real thing.
They're not real there.
Yeah.
Not really there. No, they are real particles. They're anti in the sense of opposite. So they're particles that have the same mass, but all the other properties are exactly opposite. So, for instance, the electron has an antiparticle known as the positron. The positron has exactly the same mass as the electron, but it has the opposite electric charge. It has there are other values similar to electric charge that describe how the particle interacts with other forces.
So in principle,
and they're opposite as well.
So in principle, we can use the same way we use electricity, so electrons to generate electricity. We could use positrons to generate electricity, but it just be in the opposite direction. Is that
in principle? Yes.
In principle.
The problem with that is that antiparticles, when they meet their corresponding particle, the two will annihilate and disappear. And just give off energy in the process. So, in principle, absolutely, we could use positrons to conduct electricity. But if we did that in ordinary circuits, then they would immediately interact with the electrons that are there in the circuit as well.
So you could produce a lot of energy and possibly blow up things by doing that.
If you had enough positrons, yes, certainly.
Okay, I did want to ask you about photons, because I've heard they belong on the Standard Model. Well, do they? What are they?
Yeah, photons are in the Standard Model. They're particles of light. So I mentioned wave-particle duality earlier. Everyone knows of light as being a wave. But because
what sense do you mean light is a wave?
So if we have an electric and magnetic field and we disturb it somehow, then waves are going to propagate through that field, just like water waves, waves spreading out on the surface of a pond.
So light basically behaves like the water waves we see on a pond.
Exactly.
In a different field.
Just in a different medium.
Okay.
Yeah. But because of the weirdness of quantum mechanics, it's perfectly legitimate to say that at the same time that light is a wave, it's also made up of this stream of particles. They're in the Standard Model, and they are massless. So you're asking about weighing the different particles in the Standard Model. Theoretically, the photon has to have zero mass. Experimentally, that's something that's actually very difficult to verify, because no matter how close you measure the mass to zero, you can never actually say that you've measured zero. There's also always going to be a certain amount of uncertainty there. But for very good theoretical reasons, we think that the photon has no mass.
They have no mass, so do all photons have the same energy, or any energy at all? Based on this first equation, E equals mc squared, requires, energy equals the mass of something. If it's got no mass, how can it have any energy?
Okay.
And do they have the same energy?
So that's a good question. So firstly, no, they don't all have the same energy. They have an energy that corresponds to the frequency of the wave, if you're thinking about them as waves. And because we're talking about light, the frequency corresponds to the colour. So essentially different coloured photons have different energies. Going back to the E equals mc squared equation, it's a little bit confusing, but we have to make a distinction between two different kinds of mass here. We've got the mass of a particle just because it exists, and that's known as its rest mass. So even if the particle isn't moving at all, then it would have this mass. But then because of the fact that energy and mass are entirely equivalent concepts, if the particle begins to move, then it's going to have energy due to its motion, which gives it more effective mass.
So effectively, if I picked up a photon and tried to weigh it, it would have no mass. But if it were moving, it would have mass.
It would have effective mass. Yes, that's right. And actually, a photon.
That's a really weird concept.
It is a weird concept, and a photon will always be moving because it's a particle of light. It in fact has to move at the speed of light. It can't be stationary.
So I couldn't pick it up and weigh it, even though I wanted to.
No, you couldn't. You'd have to be moving very fast to do it.